Hello everyone. In this tutorial and hands-on, we implement advanced generative AI based on Wasserstein GANs. Today, we're going to explore some of the fundamental challenges you'll encounter when training standard generative adversarial networks, or GANs. While GANs are incredibly powerful for generating new data, they are notoriously difficult to train. Let's dive into the most common problems. First up is a problem called mode collapse. In simple terms, this is when the generator gets lazy. It finds one or a very small number of samples that are really effective at fooling the discriminator and then produces nothing else. Instead of learning the entire distribution of the training data, for example, all the different breeds and poses of a dog, it only learns to generate, say, a single type of Chihuahua. You can feed the generator different random inputs, but it will still produce the same or very similar outputs. It's like an art forger who can create a perfect replica of the Mona Lisa, but has no creativity and can't paint anything else. The generator has collapsed to a single mode or a few modes of the data. The next major issue is unstable training. The core idea of a GAN is that the generator and discriminator compete and improve together, eventually reaching an equilibrium. But often this doesn't happen. Instead, they can get locked into a cycle where they just undermine each other. For instance, the generator might find a weakness in the discriminator and exploit it. The discriminator then learns to patch this weakness, but in doing so, it might change so much that the generator's previous progress is completely undone. The result is that their loss values, which you see on a graph, will swing up and down wildly and never converge. The quality of your generated images can get better, then worse, then better again, without ever reaching a stable, high-quality state. A related problem is vanishing and flat gradients. This typically happens when the discriminator becomes too good too early in the training process. It gets so skilled at telling real from fake that its confidence level is always near 100%. To understand this, think of the gradient as the slope of the loss function. This slope tells the generator which direction to go to get better. When the discriminator is too confident, this slope becomes very close to zero. It becomes a flat gradient. This means the feedback signal sent to the generator vanishes or shrinks to almost nothing. The generator gets no useful information about how to improve. It's like a harsh critic who just says, "Your work is terrible," but gives no constructive feedback. The generator's loss stalls, it stops learning, and you're left with a poor generator that can't get any better. This brings us to a crucial point about GANs. The loss values don't mean what you think they mean. In a typical deep learning model, you want to see the loss go down, as that signals the model is improving. With GANs, this is not the case. The generator and discriminator losses simply reflect how each player is doing in their game against the other at that moment. A low generator loss could mean the images are great, or it could just mean the discriminator is currently bad at its job. You can have a GAN that produces beautiful, high-quality images, but its loss values might be high or oscillating. Therefore, you can't just look at the loss curve to know if your model is working. You have to constantly look at the images it's generating. Finally, even if your GAN seems to be working, it's hard to prove it objectively. How do you put a number on creativity or realism? There's no simple metric like accuracy to tell you if you have a good GAN. Researchers have developed sophisticated metrics like the Fréchet Inception Distance, or FID, which compares the statistics of generated images to real ones, but these aren't perfect. Ultimately, evaluating a GAN still requires a combination of these metrics and careful visual inspection by a human to judge the quality and diversity of the output. It's as much an art as it is a science. Understanding these challenges is the first step to overcoming them and has led to the development of many newer, more stable GAN architectures. And remember, the whole code for this tutorial is available on our GitHub page. You can find the link in the description of this video. We've all faced the classic frustrations with standard GANs. The training is unstable, the generator suffers from mode collapse, and worst of all, the loss value doesn't really tell you if your images are getting any better. But what if there was a better way? Enter the Wasserstein GAN, or WGAN. Its power comes from a completely new loss function inspired by a clever idea called the Earth mover's distance. This forces us to change how our models think. We no longer have a simple discriminator that guesses real or fake. Instead, we have a critic that gives each image a score of how real it thinks it is. So how do we actually code this? It's surprisingly elegant. The entire Wasserstein loss can be implemented with a single simple formula. The loss is the negative mean of the label times the score. Let's see how this one rule works. Remember, our labels are now +1 for real and -1 for fake. When the critic sees a real image, the label is +1. The formula becomes -1 times score. To minimize this loss, the model has to make the score a large positive number. When the critic sees a fake image, the label is -1. The formula becomes -1 times score, which is just the score itself. To minimize this, the model must make the score a large negative number. This one simple equation naturally fuels the entire training process. Now let's see how it applies to our two players. This slide breaks down the entire process. At its heart, the WGAN is a tug-of-war between the critic and the generator. On one side, we have the critic. Think of it as a tough but fair art critic. Its goal is simple: make the scores for real and fake images as different as possible. It looks at a real image from our dataset and works to give it a very high score. Then it looks at a fake image from the generator and tries to give it a very low score. The critic's objective is to maximize this difference. The bigger the gap, the better it's doing its job. On the other side, we have the generator. Think of it as the artist, constantly working to improve and fool the critic. The generator's only goal is to create fakes that receive a high score. Its loss function is a very clever trick. The generator works to minimize the negative of the score the critic gives its images. And as we know, minimizing a negative value is the exact same thing as maximizing the positive value. So it's actively trying to get the highest possible score, directly fighting the critic's goal. This constant tug-of-war is the magic of WGANs. But for all of this elegant math to work, there's one final crucial rule we must follow. This rule is called one-Lipschitz continuity. It sounds complicated, but the idea is simple. The critic is not allowed to change its output too wildly. Its response landscape must be smooth. Think of it like a road. You can have hills and valleys, but no vertical cliffs. Mathematically, this means the magnitude of the critic's gradient must be at most 1. This constraint is essential because it's what allows our tug-of-war loss to properly estimate the true Earth mover's distance. So, how do we enforce this? There are two popular methods. The original paper used weight clipping, which is simple but can be problematic. The modern preferred method is the gradient penalty. Here, we add a new term to our critic's loss that directly encourages its gradient norm to stay close to 1. This approach is far more stable and is the standard for high-quality WGANs. So, what's the big payoff for all this? Well, this new loss structure, the tug-of-war combined with the Lipschitz constraint, solves our biggest problems directly. First, it fixes the vanishing gradient problem. This push-and-pull dynamic ensures the generator always receives a clear, useful signal to learn from. Second, the loss finally means something. In a WGAN, when you see the loss value improving, it generally correlates with better-looking images. You can finally trust your metrics. And finally, All of this leads to far more stable training, which means less mode collapse and a much more diverse set of high-quality results. It's a more elegant and powerful way to train generative models, and it's the foundation we'll build on for even more advanced techniques. Again, welcome to a deep dive masterclass on one of the most important and influential advancements in the history of generative adversarial networks, the Wasserstein GAN with gradient penalty, or WGAN-GP you've ever tried to train a standard GAN, you might have run into problems like mode collapse or unstable training. The WGAN-GP was a groundbreaking solution to many of these issues, enabling more stable training and leading to higher quality image generation. In this comprehensive tutorial, we are going to build a complete WGAN-GP from absolute scratch using PyTorch. We will construct a deep convolutional generator in Critic, prepare the high-resolution Celebi dataset, and then write the unique WGAN-GP training loop, paying special attention to the crucial gradient penalty term. We'll also integrate professional tools like weights and biases for experiment tracking. This is a long-form, detailed guide where we will explain every file, every function, and every line of code. By the end, you will not only have a working GAN that can generate realistic faces, but you will also have a deep theoretical understanding of what makes WGANs so powerful. Let's get started. Let's begin our code walkthrough with the foundation of any well-organized machine learning project, the configuration file src-config.py. By defining all our important parameters in one place, we make our project clean, readable, and incredibly easy to experiment with. If we want to try a different learning rate or a larger batch size, we only need to change it here. Let's look at some key parameters. We have our learning rate and the beta values for the Adam optimizer. These specific values of 0.5 and 0.9 are often recommended for more stable GAN training. Now, here are two of the most important hyperparameters for our WGAN-GP. First, Critic cycles. This is set to 3, which means for every one update to our generator, we will update our Critic 3 times. In the WGAN framework, it's critical that the Critic is very well trained and provides accurate feedback to the generator, so we give it more training steps. Second, gradient penalty lambda. This is the weighting factor for our special gradient penalty loss term. A value of 10 is the standard recommended value from the original WGAN-GP paper. We also define our model dimensions, like the z-dim, which is the size of the random noise vector we'll feed to the generator, and the base channel depths for our convolutional layers. Finally, we have our data and environment settings, including a convenient toggle to enable or disable logging with weights and biases. Next up is src/utils.py, our toolbox of essential helper functions. First, we have initialize weights. Just like in the basic GAN, this function applies a specific weight initialization scheme recommended in the DCGAN paper. This is a crucial step for helping our deep convolutional networks train stably from the beginning. It sets the weights of convolutional layers from a narrow normal distribution and initializes the weights of batch normalization layers. Second, show tensor images. This is our visualization function. It takes a batch of image tensors from our generator, which have pixel values between -1 and 1. It then denormalizes them back to the 0 to 1 range, arranges them into a beautiful grid, and displays them using matplotlib. Crucially, if we have weights and biases enabled, it also logs this grid of images directly to our experiment dashboard. This allows us to scroll through our training history and visually see how our generator's image quality improves over time. Finally, we have save checkpoint and load checkpoint. These functions are vital for long training runs. Save checkpoint takes our models and optimizers and saves their complete state to a file. Load checkpoint does the reverse. This allows us to stop and resume training at any time without losing our progress, which is absolutely essential when training can take many hours or even days. Now, let's look at how we handle our data in src/dataset.py. We're creating a custom PyTorch dataset class. This is the standard way to interface any custom data source with PyTorch's powerful data loader. A custom dataset class needs three special methods. First, the init constructor. When we create an instance of our dataset, this method runs. It takes the path to our image directory and a limit on the number of images to use. It then walks through that directory and creates a list, self.items, containing the full file path for every single JPEG image. Second, the len method. This one is simple. The data loader needs to know the total size of the dataset, and this method just returns the length of our self-items list. Third, and most importantly, the getItem method. The data loader calls this method whenever it needs to fetch a single item from the dataset. It gets passed an index IDX. Inside, we perform all our pre-processing for that one image. We open the image file using the PIL library. We resize it to our target image size, which is 128 by 128 pixels. We then convert it to a NumPy array and transpose it from the standard height by width by channel format to the channel by height by width format that PyTorch expects. Finally, we convert it to a PyTorch tensor and normalize the pixel values from the 0,255 integer range to a 0,1 floating point range. This pre-processed tensor is what gets returned. Now for the getSeleba data loader function. This is a fantastic automated script that handles the entire data pipeline for us. The first thing it does is call KaggleHub.datasetDownload. The KaggleHub library is a convenient tool that allows us to download datasets directly from Kaggle within our Python script. You'll need to have your Kaggle API key set up for this to work. This line downloads the entire Seleba dataset to a local cache directory. Next, since the downloaded directory structure can sometimes be complex, the script has some logic to automatically walk through the downloaded folders and find the exact path to the directory that contains our JPEG images. It also intelligently handles the case where the images might be inside a zip file. It checks for the existence of img-align-seleba.zip, and if it finds it, it uses Python's zip file library to automatically extract all the images for us. Once it has the final IMG path, it creates an instance of our custom dataset class that we just reviewed. It then wraps this dataset object in a PyTorch data loader. The data loader is what will actually feed the data to our model during training. It handles creating batches of the specified batch size, shuffling the data every epoch so our model sees the images in a different order, and using multiple CPU workers to load the data in the background, ensuring our GPU is always fed with data and never sitting idle. Let's move on to the exciting part, src/models.py, where we define our two competing networks. First up is the generator. Our generator is a deep convolutional GAN, or DCGAN. Its job is to take a flat, one-dimensional noise vector of size zdim and skillfully upsample it into a 3-channel 128 by 128 pixel image. It achieves this using a series of conv transpose 2D layers, which are essentially the reverse of a standard convolutional layer. They increase the spatial dimensions of their input. Let's trace the architecture. In the forward method, the first thing we do is take the input noise vector and reshape it into a 4-dimensional tensor with a spatial size of 1 by 1. This is the format our convolutional layers expect. This 1 by 1 image is then passed to our sequential model. The first block upsamples it to a 4 by 4 feature map. Each subsequent make-gen block then uses a stride of 2 to exactly double the spatial dimensions, going from 4 by 4 to 8 by 8, then 16 by 16, all the way up to 64 by 64. Notice how, as the spatial size increases, we decrease the number of channels. The make-gen block helper function is a standard DCGAN block, a conv transpose 2D layer followed by a batch norm 2D for training stability, and a ReLU activation. The final layer is a conv transpose 2D that takes the 64 by 64 feature map, upsamples it to our target size of 128 by 128, and sets the number of output channels to 3 for red, green, and blue. The very last step is a TON activation, which ensures our output pixel values are in the range -1 to 1, matching our real data normalization. Now, for the other player in our game, the Critic. In WGANs, we call it a Critic instead of a discriminator, because its job isn't to output a probability between 0 and 1, but rather to output a raw score indicating how real it thinks an image is. A higher score means more real. Its architecture is a beautiful mirror image of the generator. It's a standard deep convolutional network that takes a 3-channel 128 by 128 image as input and progressively downsamples it. Each make-crit block uses a conv2D layer with a stride of 2 to halve the spatial dimensions, from 128 by 128 all the way down to a 4 by 4 feature map. At the same time, we double the number of channels at each step, which is a common pattern in CNNs for extracting increasingly abstract features. Let's look at the make-crit block. It contains a conv2D layer. Then, instead of batch norm, we're using instance norm 2D. This is a choice often made in GANs as it normalizes features per image, which can sometimes improve results. For our activation, we use leaky ReLU, which, as we discussed, is a GAN staple that helps prevent dying gradients. The final layer is a conv2D that takes the 4 by 4 feature map and collapses it down to a single 1 by 1 output channel. The forward method then takes this final feature map and flattens it into a single score for each image in the batch. This score is the Critic's final verdict. Now we move to the source/trainer.py script. To keep our code clean and organized, we've encapsulated all the training logic inside a trainer class. Let's start with its init constructor. When we create a trainer object, we pass in all the essential components we've built so far: our generator and Critic models, their respective optimizers, and the data loader. The constructor simply stores these as instance variables. It also initializes a cur step counter and lists to keep track of our losses. Then we have a check for WANB enabled. If this is set to true in our config, it calls the init WANB helper method. This is where we set up our experiment tracking. WANB init creates a new experiment run in our project. We pass our entire configuration dictionary to it, which is fantastic because it means all our hyperparameters will be saved and logged automatically with the run. The WANB.watch calls are also incredibly useful. They tell weights and biases to monitor our models, and it will automatically log things like the distribution of gradients and weights over time, which can be invaluable for debugging. Before we look at the training steps for our models, we need to understand the heart of the WGAN-GP algorithm, the gradient penalty. This function looks complex, but the idea is simple. For the Wasserstein loss to work properly, the Critic must have a special property. Its gradient should have a norm of 1 everywhere. Enforcing this everywhere is impossible, so the WGAN-GP paper proposed a clever solution. Enforce it on points sampled randomly along the straight lines between pairs of real and fake images. Let's walk through the compute or gradient or penalty function. First, we create a random tensor alpha with values between 0 and 1. Second, we use this alpha to create mixed images by linearly interpolating between our real and fake images. We also set requires grad true on these new images because we're about to calculate gradients with respect to them. Third, we get the critic's scores for these mixed images. Fourth, and this is the core of the function, we use torch.autograd-grad. This is a powerful PyTorch function that explicitly calculates the gradient of some outputs, our mixed scores, with respect to some inputs, our mixed images. This gives us the gradient of the critic's output with respect to its input. Fifth, we calculate the L2 norm of this gradient for each image in the batch. Finally, we compute the penalty itself. The penalty is the mean squared distance between our calculated gradient norm and our target value of 1. We then scale this by our gradient penalty lambda hyperparameter. This last term will be used to punish the critic if its gradients deviate from having a norm of 1. Now let's look at how we train our critic in the _train_critic_step function. A key feature of the WGAN-GP training process is that we train the critic more frequently than the generator. That's why this function contains a for loop that runs for critic cycles iterations, which we set to 3 in our config. Inside this loop, for each of its training steps, we first zero the critic's gradients. We generate a fresh batch of fake images from the generator. And again, notice the crucial .detach call here. We are only training the critic, so we must prevent gradients from flowing back to the generator. We then get the critic's predictions, or scores, for both the real images and the fake images. Next, we call our compute gradient penalty function using these same real and fake images to get our gradient penalty term GP. Finally, we compute the critic's loss. The formula is the heart of the Wasserstein GP loss for the critic. It is the mean score of the fake images minus the mean score of the real images plus our gradient penalty. The critic's goal is to minimize this loss. It does this by making the scores for real images as high as possible and the scores for fake images as low as possible, while also keeping its gradients well behaved. We then backpropagate this loss and take a step with the critic's optimizer. We repeat this entire process for the number of critical cycles. After the critic has been updated multiple times, it's the generator's turn to learn. The _train generator step function is much simpler. We start by zeroing the generator's gradients. We then create a new batch of fake images by passing random noise through the generator. Next, we get the critic's prediction for these fake images. And this is critically important. Notice that there is no .detach call this time. This is because the generator's entire learning signal comes from the critic. We need the gradients to be able to flow from the loss back through the critic and all the way into the generator's weights. Now for the loss function. The generator's goal is to produce images that the critic gives a very high score to. In other words, it wants to maximize the value of fake pred.mean. Since our optimizers in PyTorch work by minimizing a loss function, the way we achieve this is by defining our loss as negative fake prediction mean. Minimizing the negative of a value is mathematically identical to maximizing the original value. We then backpropagate this simple loss function and take a step with the generator's optimizer. This updates the generator's weights in a direction that should produce images that the current critic will score more highly. Finally, we have the main train method of our trainer class. This is the top-level orchestrator for the entire process. It consists of 2 nested loops. The outer loop iterates over our desired number of epochs, and the inner loop iterates through every batch of real images provided by our data loader. We wrap our data loader with TQDM to get a nice real-time progress bar in our console. Inside the inner loop, for every single batch of real images, we perform our 2-step training process. First, we call our _train_critic_step function, passing in the real images. As we know, This will run the Critic's training for Critic cycles iterations. Second, we immediately call our iTrainGenerator step function. This performs a single update for the generator. After both models have been updated, we move on to logging and saving. We log the losses to weights and biases if it's enabled, and update our TQDM progress bar with the latest loss values. Periodically, based on our show step and save step config values, we'll pause to visualize a batch of newly generated images and save a checkpoint of our model's state. We then increment our global step counter and repeat the process for the next batch. This Critic update, generator update, log and repeat cycle is the fundamental rhythm of our WGAN-GP training. Last but not least, we have our main entry point, main.py. This script is responsible for bringing all of our separate modular components together and starting the training process. Inside the run training function, we first initialize our generator and Critic models and move them to our target device. Next, we create our two separate Atom optimizers, one for the generator's parameters and one for the Critic's, using the learning rate and beta values we defined in our config file. Then, we call our getSaliba data loader function from our dataset script. This single call will handle the entire process of downloading, extracting, and preparing our dataset. With all our components ready, the models, the optimizers, and the data, we instantiate our trainer class, passing all these objects to its constructor. Finally, we simply call WGAN trainer train. This single line kicks off the entire training process we just detailed. The last block at the bottom is the actual start of the script. It first handles logging into weights and biases if we have it enabled, and then it calls our run training function to get everything started. To train this entire complex WGAN-GP, all you need to do is run this one file from your terminal. So let's step back and look at the incredible system we've just built. This is a state-of-the-art implementation of one of the most important GAN architectures ever developed. You have built a complete WGAN-GP from scratch, understanding the theory behind the Wasserstein loss and the crucial role of the gradient penalty in stabilizing training. You've implemented a deep convolutional architecture capable of working with high-resolution 128 by 128 pixel images. You've created a fully automated data pipeline that can download and prepare a massive dataset with a single function call, and you've done it all within a professional modular code base that includes powerful tools like weights and biases for experiment tracking. You now have a solid foundation and a powerful template for any future generative modeling projects. I highly encourage you to experiment. Go into the config.py file and see what happens when you change the number of Critic cycles or the learning rate. Try adapting the dataset. PyScript to work with a different image dataset you're interested in. Or for a real challenge, try to build on this architecture to implement even more advanced models. Thank you so much for joining me on this very deep dive. If you've enjoyed it and feel like you've leveled up your deep learning skills, please give the video a like and subscribe for more masterclass tutorials. Happy generating!